Hello. In this lesson, I wish to go over another example, maybe one or two examples as how to do Riemann sum. A lot of the techniques and the applications, the theories will be applied in this process. I hope you guys will be aware. Number one is from the definition. Right? If f is defined on this interval, in this condition, it did not have a lot of requirement for f. It just wanted to be defined. And later, you're going to see this theorem. The next theorem says if f is a continuous or if f has only a finite number of jump discontinuity. So this is a pretty useful theory, and we're going to illustrate it and see how they're being used. So in this definition, we said the intervals are being divided evenly, okay, equal width, okay? So note this specific requirement, and later on we will talk about that even if the interval is not even width, the limit will still exist for continuous functions. And we choose points, right? So on the construction of these intervals, we have x1, x2, xn. So the beginning point is A, the ending point is B, and we call the beginning point A, which is x0, x sub 0, and the last point is x sub n. So the construction of Riemann sum. All of these looks pretty abstract. I understand that. So in this lesson, I wish to explain to you how these being materialized in the process when we deal with a real question. And this theory basically says, well, with partition, right? Partition the interval from A to B into n subinterval. So A, x1, x2, x3. And from x1 is the result of A plus delta x. Okay, so x1 is A plus delta x, x2 is x1 plus delta x. Okay, so let me write it down underneath, right? So here, from this interval, you can see that A plus delta x. Okay, for best result, I recommend you write along my side. Okay, write along with me. And that's x1, right? So we done this in class. And follow me, okay? So x sub 1 is equals to A plus delta x, okay? What did I delete? Did I delete anything? Okay, all right. And x sub 2 is x sub 2, hold on, x sub 2, sorry, x sub 2. Okay, so we're getting into the details. We're getting into the details, how it's actually done and how all of these symbols are being used and what their meanings. So x sub 1 plus delta x. Okay, so I want you to see the first round. Okay, and continue that process. Okay, so x sub 3 is x sub 2 plus delta x, and so on and so forth, right? So x sub I, okay, x sub I is x sub I minus 1 plus delta x. oops, plus delta x. And all the way to x sub n is x sub n minus 1 plus delta x. Okay, so we see this pattern. I'm going to put this pattern in the table later, okay? And in class, we say that this is a this is repetitive process, right? This is a repetitive process. So if we continue to derive, substituting x1 by a plus delta x, and we plus another delta x, right? You see, this is x sub 1. Okay, this is x sub 1. This is x1, right? So this is x1. So that's how we got a plus 2 times delta x. And we continue this process, right? X sub 2, so I'm going to remove the dot. So x2 is equals to a plus delta x, a plus 2 times delta x plus another delta x. You see the substitution. That's how it's been done. You can see that process is repetitive. And so next we got this x sub 3 is equals to a plus 3 times delta x. We get to see more and more in the pattern. We get to see more and more in the pattern. Now we can remove this parentheses, right? Right. When I have these parentheses there, it's just to indicate that this parentheses is replacement of x1, and this parentheses is replacement of x2. This process continues. Eventually, we get x sub I equals to a plus I times delta x. So this process is a pattern finding. And last but not least, we're gonna have a plus, right? In the last x sub n is going to be x sub n is going to be n times delta x. Okay? To verify this is true, right? This because x sub n should equals to b. So you can substitute a plus n times b minus a divided by n, right? So you will get a plus, these are the simple algebra you can do to verify equals to b. So x, so to get familiar with these, these indexing. This process is actually is indexing, right? If you want to know what is x sub 0, because x sub 0 was also mentioned sometimes when we choose the left endpoint, right? So x sub 0 is just a. So this is the complete indexing as a, I would say as a arithmetic sequence. So this arithmetic sequence, which makes the subinterval, right? A, x1, x2, x3, and so on and so forth. All right. Break it up, right? This summation notation is also illustrated, right? So this piece, I'm going to illustrate this piece. This piece is, of course, that sum, right? So I'm going to use a table to illustrate this. Okay? So in the first interval, okay, so from a to x1, right? So you can think of this picture, you can think of this picture, right? This picture, let me do this, right? So you can see the summation. You can see the summation here. I'm going to do a screenshot. I'm going to do a screenshot and put it so you don't need to see. Just look at the partition part, okay, to see how it works. The partition part, you can see that interval, there's a pattern is being created. Okay, so A x1, right? X0, right? A is x sub 0. I hope you guys mark this on your paper, okay? As you're working along my side. So this is the first interval. Okay, I'm going to use an arrow to show you. So this is the first interval, second interval, third interval, and the ith interval, right? The ith interval, I didn't write it here, so I'm going to. Okay, the ith interval, say I'm going to write it here, right? Is x sub I minus 1, comma, okay, and x sub I. So we're really getting into the devilish details. We're really getting into the devilish details. But it's just use algebra. We just use algebra. So the ith interval, okay, so the ith interval, which is right here, right? And the last one is this piece, okay, is this piece. And of course, this point is x sub n minus 1. Okay, so this point is right there. Okay, so these are the interval in the substitution. Okay, so let me clean this up. Okay, make sure you got this, right? So these are the subintervals. And we have all those slices, right? We have all those slices. So you can see around this, we got all these work. We got all these detailed work. But in the definition, we choose arbitrarily a star point in each interval. In other words, in the first interval, we're going to choose x1 star. Second interval, we're going to choose x2 star. The index of each interval, the first one is x1, the left, the right, right? Left, right. So the right index indicating the second interval. So we choose a star point in each interval arbitrarily. Okay? We choose each star point arbitrarily from each interval, and we choose that point and we evaluate the function's value at those points. Okay, so what are these numbers? What are these numbers? Okay, these numbers are, right? These numbers are, I'm going to bring this picture over here, right? So that xi star. If you look at this picture, right? So this is the ith interval, right? So in the first interval, you pick any xi star, right? You pick a point in between. And these are the choices of the right endpoints, okay? I think I got a picture of we can use any point, any I star. Okay, so I'm gonna find that picture. I'm gonna pause and come back, okay? Because I found the picture I'm going to show. All right, so I did find the picture. So you can see these are the markings of the stars, you know. On the first interval, you choose x1 star. You can choose it arbitrarily. I want to have these physical image in your mind so you have better understanding. X2 star, it looks like the middle point, but X3 star is not a middle point, right? XI star, it looks like maybe or maybe not as a middle point, but it doesn't matter how we choose the star. if the function is continuous, okay, so I want you guys to have the theory in your head that it doesn't matter how we choose the star points, okay? This theorem on the top, it says if f is continuous on that interval of our interest, and f has only finite number of jump continuity. In other words, f is not uniformly continuous on the interval, but it has finite number of discontinuity. But that's okay. And f should be integrable, meaning that no matter how we choose the points, right? For f with a finite number of discontinuity, and we compose all of these slices, the area of these slices, we add them up, whether if we let n approach the infinity, okay, the limit exists, and the limit is going to be the same as if we choose, okay, another situation is that we not only choose x stars arbitrarily, we may choose the intervals that is not quite even. What does that mean? It means delta x could vary. Okay, so the first interval's delta x may be smaller than the delta x in the second interval. So it's uneven subintervals. But if the largest of the widths of the subinterval approaches zero, right? If it is the largest, so if delta x, if the maximum of delta x approaches zero, and all of these different choices of star, we will have the same limit, and that same limit will be defined as the area underneath the curve. And you can see in this theoretical background, we're going to choose the easiest way to find our Riemann sum. Okay, so I talk about these theoretical results, is so that we are allowed, we have the liberty to choose a way, choose a method to construct our Riemann sum. Okay, which is we're going to make the subintervals even width, the same width, okay? So that the same width, we're going to choose it to be delta x. So one of the choices to make it easy is choose even width, okay? So delta x, we're going to choose to be delta x, let me type delta x, okay? So delta x is even because theory allow us to be, we can choose even or uneven, it doesn't matter. And secondly, because we can choose the start point anywhere in the subinterval, so we're going to choose right end or left end or middle or in the middle. It turned out in most of the situation, if you choose the right endpoint, it's just a little bit easier, okay? But you can also choose the left endpoint. So take this example, okay? So take this example that this commonly used method, right? Obviously, these are, we choose the right endpoint. We choose the right endpoint, right? X1, X sub 1, all these intervals are even width. All these subintervals are even width. So on this interval from A to X1, we choose the height at f of X1. Okay, so let me mark it. Okay, I'm gonna write it down for you. So this height is f of xy. Okay, I cannot do sub 1, so f of x1, right? You can see this height is f of x1. And this height is f of x2, f of x2. Okay, and the ith one, we're going to choose the right endpoint. Okay, and so on and so forth. Because it doesn't matter, theory tells us it doesn't matter how we choose our start point. So we decided to choose the point that is the easiest for us to handle. All right, so this is how the theoretical results that help us to construct Riemann sum. Take this example, right? So the actual calculation is pretty straightforward. We typically just follow this, right? We just follow this table to construct our Riemann sum, in this example. Okay, so I'm going to bring this table with us, okay, for this particular situation. In our situation, A is -2. So this is going to be -2. -2, sorry. -2, that's our x0. And x1, what is x1? X1 is going to be, we have another relationship. I should bring that column over here. Insert column. There. Okay. So the x sub I. Okay, I'm going to repeat that. So x sub 1 is equals to A plus delta x. Okay, I'm just going to copy a delta x, right? And x sub 2 is x sub 1 plus delta x, right? But we already derived that formula, didn't we? So x sub 3, so we're deriving this second time. I hope you guys, if you find it boring and you know, but I hope that these repeats will help us understand this better, and you become more and more familiar. Okay, and x sub I is equals to x sub I minus 1 plus delta x, right? Plus delta x. You see this process, we just did it, but we're doing this again. X sub n, and that's going to be x sub n minus 1 plus delta x. So this is the, we're really just applying algebraic information, algebraic knowledge, okay, to do this. So we know x0 is -2, and we also know b is 0, right? B is 0 in this particular case. Okay, B is 0 in this particular case. And what is our delta x? We can find our delta x, right? Our delta x, I'm going to put it on the side, right here. Right, so now the details becomes more concrete, right? So x sub 1, we know that equals to A, x sub 1 equals to A plus delta x, but this is also going to be our start point. X sub 2 is also going to be our start point. X sub 3 is going to be our start point. So knowing the representation of these start points will be important. So this is going to be A times 2, A plus 3 times delta x. And this is I times delta x, and this is going to be A plus n times delta x, right? So this becomes more concrete. But what is A? A is -2. So A is -2. You can see, oh, sorry, -2. Okay, so we're going to replace A by its equal. right? What else? This is, you can see it as a 1 times delta x. So we already have a pattern, okay? x1, x2, x3, all the way to xn, and all of these x1 star, we chose it to be x sub 1, right? Even though we have arbitrary, we have freedom to choose anyone we want. We can choose left and right and, but we choose because any choice will lead to the same interval. Will lead to the same, will lead us to the same limit. So why don't we just choose the easiest one, right? So this is how we're going to choose the easy one. Okay, so then all these, the height of each slice is done and the area of each rectangle is approximated. Okay, so now you can remove the star, right? You can remove the star. You can remove the star now. And if you want to choose your, if you want to choose your left endpoint, you can do it accordingly. Okay, this is x sub I. Sorry, deleted by accident. So that's the Riemann sum after you have chosen the star, right? We already chosen that star. So that's how concrete examples is brought in the picture, So now we can brought in even more. We can brought in even more because we're going to add up all of these areas of rectangles, okay? So next, we're going to look at the summation notation. I hope you guys, from this process, you get better at using the summation notation, right? We got Riemann sum. You are familiar with the interval, the making of the interval. And so these are the concrete form, right? So learn to work with x sub I, right? We got this form. So we already know x1 is -2 plus 1 times delta x, right? So x sub I is a plus I times delta x, okay? So it's a sequence of substitutions. It's the kind of formula. And we choose the right, if we choose the right endpoint. But what if we choose the left endpoint? If you choose the left endpoint, the formula will be slightly changed, okay? I will show you that after this one, okay? Because I don't want to do two things at the same time to confuse anybody. So we choose the right endpoint. So now the x sub I becomes more and more concrete, and x sub I is going to be used in the formula. And we chose even with, so the max is not needed. Now let's construct the Riemann sum. We choose the right endpoint, and then we're going to choose this was x sub I, right? So when we put in the actual x sub I, it looks a little bit more complex, but no fear. And this is delta x, okay? Delta x, that was delta x, f of x sub I, right? So as we substitute, and we're going to plug in the function. The function is here. Okay, I'm going to put the function on the side. So basically, when we plug in x sub I, so this is going to be x sub I. Everywhere x sub I will be in place, right? And now x sub I is this piece, right? We have derived it. Maybe we remove the dot. Let's remove the dot, okay? Remove the dot. So this is x sub I. So this x sub I will be in the place of x sub I, in the place of x sub I, squared in the place of x sub I, right? You can see it becomes more concrete. Let me remove the dot. Okay, so you can see this piece is the same as that. It's just a bunch of substitution. It's just a bunch of substitution. Multiply delta x, okay? And because we use summation notation, I really encourage you guys to learn how to use this because you're gonna need this a lot in Calc 2. And then we're gonna work on this part. How do we work on this part, right? It's a plus b squared, okay? What is a? You can treat this as a and this as b, right? So a plus b squared. So let me just I put a piece of scratch paper right here for you, and you watch me substitute this in place. Okay, this is a, and this is b. Okay, so a is -2. So everywhere -2, everywhere a will be substituted. So everywhere a will be substituted by -2. Okay, b, what is b? This is a b, right? Because this is a plus b squared. This is a very commonly used algebraic formula. So b is substituted by 2 over n times I being squared. So everywhere b will be substituted by its equal, which is that piece. And this b will be substituted, but it needs to be squared properly. See that how the basic algebra is used here, okay? And the second part, of course, that's just a direct substitution of x sub I. Okay, so on this part, you will see in the next step, you see -2 squared. You see I put a -2 squared plus 2 times -2ab, right? 2ab, a squared plus 2ab plus b squared. So this piece, okay, this piece is the same as, okay, let me box it temporarily, okay? It's the same as that piece. It's just the basic algebra being used, okay? They're really just basic algebra being used, okay? On that part, because there's a plus sign in front of it, I just simply remove the parentheses. I just simply remove the parentheses because there's a plus sign in front of it. So that's how you see this. There's a -2, right? Plus -2. You can see the correspondence, right? So now I'm removing all of these because it's going to be in the recording. You can always come back to watch it. And then what do we do? This is delta x, right? We're going to combine like terms, right? This piece, -2 squared is 4, right? And 2 times -2, that's a -4. We got -4 here. And 2 over n times I. So this part can be further simplified. We're going to see in the next step. We're going to see the next step. On this piece, okay, we're squaring 2 over n, and we're squaring I. Okay, so we got that. I'm doing very carefully. I'm sure you probably could do it faster. Okay, I just want to show more details to you. You can see these are just really basic algebra. So -2 and +4 combine into 2. And this piece is a -8 over n. And this is a +2 over n times I. These two are like terms. So this piece and that piece are, I'm sorry, never mind, sorry. This piece and this piece are like terms. So we got a -6 over n times I plus, when we're squaring this part, we get 4 over n squared times I squared. I removed the dot, I removed dot. So by this time, I was just processing the inside of the bracket, the inside of the bracket. Okay. And by this time, what do we do next? Well, we want to separate the summation, okay? But before we do that, we have to make it inside the summation, only adding or subtracting. I took 2 over n times 2, that's a 4 over n. 2 over n times 6 over n, that's a 12 over n squared I, plus 2 over n multiply 4 over n squared. We got n over 8 over n to the power of 3 I squared. And then we separated these 3 summations into, this is one single summation into 3 summations. We can process it even further. On the first summation, right? It is just we can distribute it, and these properties about summation you have it in your index card. So let me just to quickly remind you. Okay, those index card summation typically look like. Oh, do I have this index card? Yes, I think we do have it. I'm gonna find it for you so that, wait. I don't know. It might be faster if I type it. Okay. The summation operation, right? The summation operation, you will see the for summation, right? The properties we have that a sub I plus b sub I is equals to a sub I, b sub I, and the summation is coming along with. So one summation notation, if it's addition, can be turned into, in other words, the sum. Okay, the summation of sum is the sum of summation. The summation of difference, right? If it's adding or subtracting, is the difference of summation. Okay, and the constant. Okay, suppose you have a big fat constant here, right? You have big fat constant here, a sub I, right? And you can bring this constant outside. We can bring this big constant outside the summation. But what makes the constant? Constant is defined as anything that is not dependent on the variation of I, because we know that I changes, I 1, 2, 3, 4, all the way to n, right? So in this case, you have a constant, you can pull it out because C should have nothing to do with I. Okay, and the third property that we're going to use that if we do summation of 1, what would that be? Well, that equals to n, right? But if we have a constant C, and that's going to be C times n, right? So these are the formula related to summation. We don't have a multiplication or division of summation because that will get into really, really complicated, okay, situation. There cannot be a formula, okay? There cannot be a formula for our use. So once we separate it into these 3 summation, what do we do next? What do we do next? We're about to use these properties, okay? We're about to use these properties. And first, look at the first summation. Look at the first summation. In the first summation, 4 can be treated as a constant. Okay, I'm going to write an extra step. Okay, I'm going to write an extra step to show you the process. 4 can be treated as a constant. Okay, so I can bring the 4 outside. 1 over n can also be treated as constant. Why? Because n has nothing to do with I. Okay, n is considered, has nothing to do with I. That's why we can bring n outside as well. So we just have 1 left, right? So we use this formula 1, this equals to 1, so this equals to. We got into a situation that this piece is turned into n, because that means this piece means what? Okay, this piece means 1 plus 1 plus 1, how many times? Plus, okay, plus 1 n times. Okay, so let me mark it for you. N times. So this summation notation means that, okay? You don't need to show me, okay? On the second one, so that's how we get this piece. That's how we get this piece. The second piece, once again, 12 over n squared can be treated as a constant. 12 over n squared can be treated as a constant. And for the same reason, they don't have anything to do with I. So we bring them out. So we use the second property. Okay, the third one is that 8 over n to the power 3 will be treated as a constant. So for the same reason, so that's how we take all of these constants outside. Okay, so you can see in this paragraph, I know this it could look, overwhelming, but if you need to go back to watch it again, right? So I'm going to just, should I save this? Yeah, let me just save this for you. Okay, let me just save it for you. And put this piece over here. Okay, all right. So we have all these summation properties. These are summation properties that you need to use. But anyway, so I'm going to remove this. So now at this moment, you know what we're getting into, right? So this is the moment of, we're almost there, right? So this will lead us to equals to 4 minus 12 over n squared. And what is this piece? This piece, we have a formula in the index card, and that is equals to, for I equals to 1, we get 1. I equals to 2, I equals to 3. That's what it means. That's what it means, all the way plus n. And we have a formula. Okay? That's going to be n times n plus 1. You should find that formula in your index card. If you don't, let me know. Okay, so that piece will be replaced by that. Okay, the last summation is that we keep the constant outside. And what is this guy? This guy is equals to 1 squared, right? Is I squared. As I varies, So when I varies as I equals to 2, this is going to be 2 squared, plus when I equals to 3, it's going to be 3 squared, you see? And plus, we add them all the way to n. That's when I equals to n, so that's n squared. So this sum, also we have a formula. That formula is n times n plus 1 times 2n plus 1. It's a formula you might have derived from your pre-calculus class. But if you have forgotten, there's no fear. You should find it in your index card, okay? If you don't find it in your index card, please do let me know, because I might have taken some, we can put it back in. All right. So by this time, we can really start taking limits, okay? So I'm going to put all of these, I'm going to put these formula, okay, for your consumption, right? I'm going to remove these though, okay? Otherwise, it's just not enough space. I'm going to take these formula and put it here for your consumption. And right there, okay? And removing these, right? So these formula, when you need it, you can use it. You don't need to memorize them. You don't need to memorize them, okay? So for all of these work, we have gotten to the point. We've gotten to the point that we got the Riemann sum, right? All through all these steps. It could be shorter, right? From all these steps, we finally got to this place. We finally got to this place. And we know that, the step 1 is partition, step 2 is making the Riemann sum, and we are here by choosing the right endpoint. And of course, the next step, we're going to find the limit as n approaches infinity. Infinity n, right? Infinity on n. So we're going to take this limit. So we're basically going to work on this limit for this piece. There we go. All right. And then can we take limit piece by piece? Well, to apply that limit law, we have to guarantee every little piece, the limit exists. Therefore, we need to do some algebraic manipulation, okay? Manipulating, algebraically correctly. Okay, so I'm going to show you how we do that. All right, 12 over 2, that's going to be left up with 6. So this is 2, it's just 1. N squared, n, so one of the n can be taken away. So we just have n. So how about I bring this n to here, right? So I just have 6 left. On this piece, I'm going to write it as 1 plus 1 over n. That's a simple algebraic manipulation, right? And on the last piece, wait, did I forgot the formula? Oh, yes, I did. I forgot to put this formula in place. That was a terrible mistake. Okay, I'm sure you saw it. But how did I get away with it? Well, I only got away with it because you're not around, right? So now I need to put it back in. Okay, I apologize for that. And next, we're going to reduce, right? So I'm going to bring the n to the power 3 under and bring the 6 over here and feel free to reduce it. So that's 3 under 4, no problem. So 6 is gone. And n to the power 3 can be turned into, we reduced one of the n from the top. So this is n to the power of 2. Let me make the fonts just a little bit larger. Okay. And focusing on this limit. And what are we going to do with this piece? Right? On this piece, I'm going to part it into n squared is going to turn into n times n. One of the n is going to divide into this piece, which I'm going to get 1 plus 1 over n again, right? So that piece and one of the n is gone. And on this piece, I'm going to take the n divided into the parentheses. So I will get 2 plus 1 over n. Okay, so as n approaches infinity, 4 is a constant. It has a limit 4. As n approaches infinity, 1 over n approaches 0. As n approaches infinity, 1 over n approaches 0. 1 over n approaches 0. So that our next step, our x step is taking limit. We're taking limit. Okay, so limit is still, excuse me, is still used here. So by taking limit, this limit is 0, this limit is 0, this limit is 0, right? So the rest is just arithmetic. Arithmetic. What do we get? What do we get? And this is going to be 6 left, and this is 1, and this is a 2, right? So this is going to be 2 times 2, and we're almost there, right? So this will give us a -2. One more step, just one more step, okay? Because I don't like to make mistakes. So this is a -2, and this is 8 over 3. 8 over 3. All right. And then what do we do? Well, common denominator, common denominator. So -2 will turn into -6 over 3. Okay, so finally, we got -6 plus 8. That's going to be 2/3. All right, okay. Well, how do we know if we got it right? How do we know if we got it right? Well, we have fundamental theorem of calculus part 2, right? And we can use that to verify if we got the right answer. Okay, so verify answer using fundamental theorem of calculus part 2, right? So what do we get? What do we get from here? The antiderivative. The antiderivative of x squared is 1/3 of x raised to the power of 3 plus the antiderivative of x is 1/2 x squared. Okay, all of these will be evaluated at -2, 0. Okay, so we're going to do that. Let's see how we're going to do that. Okay, please look at your index card of fundamental theorem of calculus part 2. So capital F of B. B is 0, right? So all of these in the bracket will be Okay, the bracket on this will be, we're going to plug in the b, which is 0. On the second part, we're going to replace x by -2. Okay, replace x by -2. All right, and of course, all of these, the first part is 0. The first part is, I'm sorry, first part is, wait, I meant to copy. Where's my mouse? Okay, here. All of these is going to be 0, right? Gone, negative. So we're going to work with the inside of this bracket. -2 to the power of 3, that's going to be -8, right? So that piece is turning to -8. And this is +4. +4 divided by 2 is going to be a 2. Okay? And then I'm going to open up the parentheses. Okay, I'm going to open up the parentheses. So I've opened up the parentheses, negative, oh, is positive, -2. So this is the same situation as we had here, right? Because we can just accept that this is moved to the back part. So we got the right answer. We have got the right answer. So this is the general process of doing Riemann sum, which is a great practice for you for all of the algebra courses you have taken but forgotten, and if you only want to do the algebra related to calculus, and this will be a perfect opportunity to practice it. Of course, you know, we're not going to touch you on this, but you need to have certain familiarity with these knowledge and the skills for your next course. Okay, I don't mean to make this too long, and thank you for watching, and I might make another one, and thank you for watching.